All right, let's go ahead and get started, just so we don't wind up cutting too much into when the festival begins. This is their practice. They're like pre-practice, so I imagine things are about to get really noisy out there. So I'm John DeGoes, and obviously I like free monads because I talk about them all the time, and I blog about them, and I encourage people to use them, and I've gotten tons of companies to using them. I've even inspired some of the free monad libraries out there, so I'm the free monad guy. On my tombstone is going to be, he was a free monad, or something like that.
Kind of a big deal.
Exactly, kind of a big deal. So this is what we're going to talk about tonight, assuming we don't get drowned out by the music festival. I'm going to do a whirlwind tour of the free monad that you may not have seen before, because it's a development of the free monad from first principles, which will hopefully give you new insight into it if you're a little bit shaky on what it is and what it means. And then I'm going to show you some of the really cool things that you can do with a free monad that you can't do with other techniques, or in one case that you just can't do easily. It's really, really hard to do. And then I'm going to show you where the free monad goes off and sort of crashes and burns. And that's going to be interesting, because living with free monads for a couple years, as I have, I've encountered problems you just can't solve with them. At least you can't solve in any practical way. And that's one of the sides that not a lot of people are talking about, because you have to have used these beasts in the wild for a while before you run into that sort of brick wall that does not permit passing. And then I'll spend the rest of the talk discussing ways we can possibly fix what's wrong with the free monad. And it's not really fixing what's wrong with the free monad so much as it's moving past. It's moving past the free monad into something that logically succeeds it, and that allows us to do much, much, much more without sacrificing all the benefits of the free monad. There's not just one way to do it, so I'll cover a few different ways. And each has its own pros and cons. And as a result, at the end, I'll have just some closing thoughts on what does all this suggest about the future of using free-like structures in programs, and where might it lead in the future. So let's try to go back to square one and pretend we've never seen or heard of a free monad. We're trying to interact with the outside world. We want to do effects. We want to do things that are not, strictly speaking, pure mathematical functions. Pure mathematical function returns a value for every input. It always returns the same one, and it has no external effects. That is, the computation of the return value is the only effect of applying the function. And that doesn't hold for some programming functions, right? When you call readline, you don't supply it any parameters and you get back a string. And then the next time you call readline, you get back a different string, and so on and so forth. These are not mathematical functions, they're not pure functions. And as not pure functions, they have the sort of issue that they're harder to reason about, because they return random stuff all the time and they mutate stuff and whatnot. Hard to test because you send them one value and you get something, you send them the same value another time and you get something else. And in general, as functional programmers, even though we have to use these functions, and we do, we try to minimize their use. So what if we were trying to push the boundary of what we could do without actually executing effects? What might that look like? Well, one possible solution would be to define a data structure to represent a description of those effects. In other words, we convert actually doing effects into building a data structure that describes the effects. Now, for purposes of making this easy to follow, let's pretend our program only needs one effect, and that effect is writing a line of text to the console and reading a line of text from the console. And we can build lots of interesting, useful programs just with that basic machinery, and you can see how this approach can be generalized later. So if we were trying to do that, then here's how we might do that in both PureScript and Scala. We might have a data structure called console.io, and that can either represent the effect of writing a line, as well as the continuation of the program, that's the rest of our program, So that's why WriteLine takes two parameters. It takes the line of output we want to write, and then it takes the rest of the program, that is the stuff we want to do after we've written that line of output. And then another effect is reading a line. And for reading a line, we store a function. And that function wants to be fed a string. And if you give it a string representing the line of input read from the console, it will give you the rest of the program. And then finally, just so we don't read and write forever and ever and ever, we need a way to stop this process, so we have an end constructor for our data type, which allows us to say, okay, this is the end of the program. We no longer wish to read or write things. So this is a very simple data structure, and it's very simple, or relatively simple to understand. And it captures the structure of effectful computation for console I/O. Because I can build programs using this that say, read a line, and then I'm going to pass a function that takes the line read, and then I'm going to return write line, and it's going to say hello, and then it's going to concat the thing that was read and say hello someone. So you can run that program, or at least in theory you could run it, and type in your name, and it would say hello John back out at you. So I hope you can see that this data structure actually describes the class of effectful programs that only require console input and output. And there's one sort of small problem with it, and it's not composable. If we have two of these console programs, there's no real easy way to smash them together. We can do this one and then do that one, or we can do that one and do this one, but there's no way for this one to generate a value that can be used by this one, because when these programs end, they don't return a value. Because that end data constructor, it doesn't accept a value. So after we've evaluated this data structure and gotten to the end of the world, we have nothing to return. But that's easy to fix. All we have to do is introduce a type parameter called A here and thread that through all the constructors. And now our end constructor becomes end with, and that's the value we end our program with. So console I/O of A is a console program that returns a value of A. So this is pure. Like if you return a program, if you create programs that use this, all they're doing is returning a data structure, and it's totally deterministic. We've converted a problem of, oh my goodness, how are we going to model effects in this world that requires us to do things with the outside world while still preserving the integrity of the mathematical functions we would like to build our programs from. Yeah? Is there a possible formula,
like is the and or end with required to be a member of the operations, or could you formulate like the continuation as like a maybe, could it be like maybe console IOA, and then you'd have something to know like, hey, I'm done, or I should keep going?
Yeah, it could be like an either of the terminal value, or yeah, it could be an either of an A or a console of A, and then you could delete the end with constructor.
Gotcha. And if you get the left, that means you're done, effectively.
Exactly, right. So there's one more thing we might want to do with these programs, and that is, if we have a program that produces, say, an integer, maybe we want to take that program and turn it into a program that produces a string in an easy way. Of course, we can dig into that data structure and recreate it, and then end up changing the value that way. But it's just as easy to extend our little data structure here with a map operation that allows us to turn a console of A into a console of B by supplying a function from A to B. And if you know about functors, well, this is what allows console I/O to be a functor. This is what it looks like in Scala, same thing. Just a new data constructor called map there that allows you to change the value of the program. All right, well, this is a little complex, and moreover, it's not composable. That is, if we were to do the same thing for file I/O, for example, then we'd run into a problem. We can either have a program that does console I/O, or we can have a program that does file I/O, but not both. No real way to solve that problem using this approach. There isn't. And also, if you notice, if we were to create that file IO data structure to describe file effectful operations, it would have an end with and a map, wouldn't it? And that's just boilerplate. And also, its operations, whether they're read file operations or write file operations, they would always have a constructor parameter representing the continuation of the program, the rest of the program. And that's boilerplate. So it would be really nice to eliminate that. And here's how we do it. First, we take this one step of introducing a chain operation that allows us to sequence two operations, where the second operation depends on the result of the first. And this is bind/flatmap, represented as a data structure. But you can think of it as literally, we have our program, we have a function which takes the value produced by that program and turns it into another program, and we can stuff these two in the chain constructor to say, okay, we're encoding the fact that the second program depends on the value produced by the first program. So we haven't changed a whole lot. It looks almost the same here. I've changed end with to be this operation called pure. And then I've deleted the continuations in write line and read line, and instead just created a hole there called A. And that's the reason that I needed a pure, is so you can stuff anything you want in there. So when you create a write line using the write line constructor, you can stuff anything you want in the A hole. It could be a you can. My wife's a doctor and she'll attest to that fact. But it could be the continuation of the program. But it also could be something like units or a constant value or whatever you like. Anyway, these types, you don't have to believe me, but if you try it, you can, using these types, you can construct programs that are equivalent to the preceding definition. You just construct them in a different way. And it's not obvious why. It will be soon. This is what it looks like in Scala. Same thing. We have the chain data constructor and the pure data constructor. And now, notice something about this. Write line and read line don't have any of that continuation stuff, or at least it's been simplified. And then sort of our boilerplate has been encapsulated into this pure and chain data constructors. And that's key to doing the next step. In the next step, what we do is we introduce the free monad. And in the free monad, we basically pull out the effects into a functor, or even a type constructor of kind star to star. And then free contains all the machinery in the boilerplate. So in this definition of free, you can either take a pure value and you can lift it into a free program in F, or you can run an effect F of A, or you can chain two of these things together. And that's a very simple, relatively minimal, there's actually an even better one, definition that sort of follows directly from the types of abstractions we made in the preceding slides. It's the same thing in Scala, exactly the same, just 10 times more hideous. And now we get to, okay, this is the motivated definition of free. And if you look in where the free monad was first introduced, it was some paper, I can't remember it off the top of my head. But you actually won't find that definition. You'll find a more, a pure definition, and also a more pedagogical one, because it has certain performance problems. But nonetheless, it's nice and clean, and in fact I can fit both the pure script and the Scala version on this slide. This is the canonical definition of the free monad, and it turns out this is equivalent to the preceding one. So I can either take an A and lift it up into the free program, or I can do this operation called join, which is monadic join. But instead of actually doing the join and flattening the F of A into an F of A, I'm just storing it and saying, okay, deal with that flattening later. So it's a data structure that describes that sequential computation. So how do we interpret the free program? Well, there's a very simple way that you can interpret the type signature free F of A. This is a program that halts, runs forever, or produces an A. So this is a program whose operations, whose effects are defined by F. In one case we had read line and write line, but it could be much more complex than that. And maybe this program is going to run forever. Maybe it's going to stop. Maybe it's going to halt with some error. It could do that. Or maybe it's going to actually produce an A. That is an interpretation that is valid for all free programs. And here's how we use it to reconstruct our preceding example. We define console IO, which can either be a functor or, with more sophisticated free monads, it doesn't even have to be a functor, it just has to have something of kind star to star, be a type constructor that accepts one type and returns one type. And then we can define little helper functions to take and lift up our individual f of a's into a free f of a for reading and writing lines. And then finally we can write whole programs in this. These programs, yeah, Chris?
Sorry, you mentioned in some cases you have a functor. Do you mean operational?
Well, that does it too, right?
Kind of, but it does something different, so it's not quite one.
I was thinking of Oleg's freer monads.
Oh, yeah, sorry.
Which is basically the composition of co-Yoneda with into the free, so you don't even need, you basically have a free functor inside a free monad, and so the thing that you're working with doesn't even have to be a functor. And it just saves writing some code, especially in languages like PureScript and Scala, which don't have the ability to derive functors automatically. Okay, so in here I define programs, interactive programs, which are doing nothing but building data structures. That's all they do. They don't interact with the outside world. They just build data structures. And here's how I would do the same thing for file I/O. I would define the operations that are used to build my sequential program in PureScript and Scala, both reading from the file and writing to the file. And then this is sort of a magical trick of the free monad that's not possible with our earlier, more naive definition, and that is I can take advantage of the fact that if I have two functors, I can combine them together to get another functor. And how this works in my favor is I can define coproduct of f and g to be a functor where both f and g are functors that consists of either the left effect or the right effect. So either it's one effect or it's the other effect. And when I do this, I can define programs in free that use the coproduct of two effects. And so now I'm able to basically compose effectful programs. I can have one program over here that does these effects and one program over here that does these, and I can compose them together into a program that does all of the effects. And so this allows me to reuse this same machinery down in certain parts of my program. They only use a few effects, but as I sort of build it up, eventually I need more effects, but occasionally I might be able to eliminate some effects by expressing them in terms of others, etc. And it gives me this ability to compose programs with arbitrary effects together to get something of the same structure and shape. So, why free? Why go through all this? Well, there's one reason, and that is, obviously, this allows us to make effectful code pure code. And there are some benefits to that. But actually, there are more practical benefits because there are lots of other ways to make effectful code pure code. No specific reason why you would have to use free to do that, because we have other abstractions like the IO monad in Haskell, and we have F and AF in PureScript, and we have task and future, and so forth in Scala. There are lots of ways we could do this. But it turns out that when you describe the effects of your program as a data structure, you gain the ability to do some things that are either not possible otherwise or are extremely difficult. And an example of that is type-safe mocking. How many people have used a mocking library? Real programmers. So in Java, mocking libraries are sort of a nightmare because in order to do it effectively, an API, Java API, could be accepting nothing and returning nothing, and doing all kinds of crazy I/O with the database and this and that. And mocking such requires you basically to rewrite the bytecode. So there are very sophisticated techniques to allow us to do that, and it's all complex beyond imagination, really, because you have to intercept all these things that are happening. But if you use free, remember, these free programs are just data structures, and as data structures you can look at them and you can see what they are. So if something is saying, I want to read a line of input, then you can say, okay, well, were we expecting that program to read a line of input right now? And so you can build a mocking library that's totally composable and totally type safe and doesn't require you changing anything, let alone instrumenting bytecode or adding stuff to the source code or all the techniques that are sometimes used in the statically typed languages to achieve the benefits of mocking. So you can get all that, and it looks simple and straightforward. It's like expect this, expect this, expect this, and you're providing the things that are required by the different operations. It's totally type safe, totally composable, really beautiful. And it's only possible using free monads or something similar that describes effects as a data structure. Another really cool thing that you can do is monad is there's many classes of programs that don't require the full power of a monad. Monad, remember, has sequentiality baked in, so the second operation necessarily comes after the first operation because it depends on the value of the first operation. But sometimes you don't need that. An example is sometimes you can do one request and do another HTTP request and another HTTP request, and you only need all three values. You don't need to do those three requests in order. And it turns out if you back up and decrease the power of a monad, basically strip some stuff away from it, you end up with something called an applicative. And an applicative allows you to express sequential or parallel operations, but the sequential operations may not depend on each other's runtime values. And there's a structure for this called a free applicative. I'm not going to go into it, but it does the same thing for applicative that free does for monads. That is, it gives you, given some functor or type constructor of kind star to star, it will give you a free applicative just by building this data structure. And think of free applicatives as being parallel computation that build data, and rather than the much more powerful sequential computation that free monads give you. And if you use this to describe a parser, for example, one of the really cool things about free applicatives is that because there is no sequence, there is no one operation that depends on the value produced by another, it means you can totally introspect that graph without actually interacting, without actually doing any I/O. Which means that you can take such a data structure and transform it to one that's more heavily optimized. You can do optimizations on your description of a program. How would you use this? Well, if you're building a parser, it's really nice to be able to allow the user to parse a single character, because then they can parse this character and that one, and you know, just sort of have compositionality all the way up. It's not so nice to run parsers that parse only a single character at a time. That has performance implications. It'd be nice if we could detect those parsing of individual characters and optimize them into parsing of a string. And in fact, we can do that with free applicatives. And that's possible, again, because we're representing the effects of our program as a data structure that we can look at and we can transform and we can do things with. And there's the same thing in Scala. And here's another really cool thing. This is one of the things that it is super clean and super easy to do this with free monads. It's possible using other techniques. It's just not as easy and not as clean. And that is aspect-oriented programming, but not the bad kind that you may have had the misfortune of using, but the good kind, the kind that's totally type-safe at compile time and super composable and has well-defined semantics. An example of that is, let's say I've got this file I/O data structure which describes file input and output operations, and I want to take a program that does file I/O and I want to log what it's doing. So I want to log every time I read something and write something and so forth. so I can track down problems in production and fix them. Like, know what went wrong, oh, the file wasn't there, I got this error, etc. Well, that's super simple with free monad. All I have to do is take and translate a single file operation into potentially other operations. And this time, in this case, I translate it to either a file I/O operation or a console I/O. So I just log to the console. And because all the operations are data structures, I can look at them and I can print out their things, and I can build really descriptive logging messages that tell me what's going on with my program. My program consists of all these operations, which are just data structures, so I can do the logging automatically, and I don't have to manually insert log lines that merely replicate what my program is expressing in other ways. And so I do that here. I take that and I basically weave the effect of logging into my program without having to touch it, without having to instrument it, and I get that across my whole program, and I can do it dynamically. So if the config file doesn't specify logging because it wants to run faster, and I don't even do this weaving, and I'm left with a much sort of higher performance version that doesn't even have to think about logging.
Hey John,
Yeah.
can you go over quickly what aspect-oriented programming is?
Yes, I can.
You
So
don't want to know.
Just briefly.
yes, aspect J. Yeah. How many people have used aspect-oriented programming? Wow, you poor souls. Even you, Chris? My.
Well, I did closure and commons before.
Oh, okay. So in aspect-oriented programming, actually, there's so many things in object-oriented programming and best design principles that, I actually look at them and I think, yeah, they're addressing real pain points. They really are. And some of the best practices that have evolved there, I look at them and think, yeah, I understand why that works in that paradigm, or what the intention of it was and what pain it's trying to alleviate. And the idea behind aspect-oriented programming is that many times our programs consists of conflated concerns and lots of boilerplate. An example of this is a single function in our program may have business logic in it. It may also have like DevOps logic in it by logging. It may also have security considerations in there and do authentication and this and that. And who knows how many other things that it might have mixed in there. And the recognition of aspect-oriented programming was, well, there are lots of different concerns that become tangled inside our code, and it would be really nice if we could pull those apart into totally independent concerns, something that was just concerned about security, something that was just concerned about logging, something that was just concerned about business logic, and then sort of weave them together. And the way that aspect-oriented programming did that was not very safe and did not have sound semantics. And also had like lots of machinery required in order to get it running. So it still isn't that widely used, but nonetheless, it was a good recognition that the way we write programs is often as conflated concerns that ideally would be totally detangled. And free monads allow you to do that quite elegantly, and also allow you to do it programmatically, in the sense that we don't have to express lots of logging logic. All we have to do is log the individual operations that make up our program, and then the composition of them will sort of be taken care of for us.
So you could use that, say, like, weave analytics into your...
Right. How many times was this method called, for example? That would be a good use of aspect-oriented programming on the front end. And even though it's not always called aspect-oriented programming, people still use it, especially dynamic languages make this super simple. Like, it's very hard to do this in statically typed languages, but dynamically typed programming languages make it dead simple. So people do this a lot because they recognize that stuffing all your things into one function across all these different concerns is not a way to maintain that. It's much easier to maintain it and to understand it and to reason about it when those different concerns have been pulled out. Anyway, free monads let you do aspect-oriented programming the way God intended. Oh, and here's the same thing in Scala, if this makes more sense to you. All right, so here's the problem with free monad, and it's the problem eventually run into once you use it long enough. The free monad is only a free monad. That's all. It's a monad. Great. It has point and it has bind. And then of course you can map it and it satisfies all the associated laws and it's an applicative and whatnot. But that's all it is. It's not a monad alt. It's not a monad plus. It's none of the other structures that we have available to us. And as a result, it's very, very difficult to do things like model parallelism with free monads or model failure. Free monad program can fail, but it cannot fail in a composable way. It's hard to do alternatives. So if you want to do, let's try this, and then let's try this free program, and then if it fails, let's try this other free program. You can't do that. It's also not possible to do non-determinism. So if you want to sort of explore lots of things in parallel and find things that work, you can't do that. And all the other abstractions that you can possibly think of that have more structure than a monad, you can't implement them with the free monad. You can't. It's just not powerful enough. It's too general. And let me give you a few examples of really cool things that we could do if our free monads were much more than just free monads. One is if we could take and issue parallel HTTP requests and get back the results at the same time. And you can't really do that. The structure of the free monad only allows sequential operations. Another use case would be, okay, well, let's basically split a co-inductive problem like an interactive user application into inductive fragments that are triggered based on user input, and then we'll basically try them all and explore the ones that work. So in this method of designing a user interface, you look for things, you say, okay, I want to click, and then I want a space bar, and then I want someone to move this over here, etc. You look for them, and they represent program fragments, and you can sort of explore them, and some of them will fail and die, and others will succeed. Well, we have the capability to express this. It's like a monad plus or alternative, and you can't do that with free monad because it doesn't possess the right structure. It doesn't possess enough structure. And then the final use case is failure at the level of, you can have local failures in free programs, but you can't have global failures at the level of the free. So you can't take two fully constructed free programs and then do this one and then do this one if the first one failed, and other types of things, and recover from failure at that level. So these are pretty big problems. And basically, if you use the free monad, you're going to run into all sorts of problems that you want more structure to solve, but you can't. So what are you going to do? Well, you're probably not going to abandon the free monad, so you end up crippling the way that you write that program and straining it. And I've seen it, having worked in the Quasar code base, for example. There are definitely some places where it's straining the limitations of the free monad. It uses free monads extensively, and it's running into those limitations. Some things could be dramatically simpler and much more reasonable and composable if only we had a bit more power. Okay, so let's talk about ways we can deal with this problem and move beyond free. And the first two solutions involve nesting. So let's take that example of issuing multiple HTTP requests. We want to be able to do things in parallel, or maybe we want to run 10 threads to do 10 different things, and we want them all to start executing at the same time. We don't want them to be sequentialized. And then we want all 10 results, and then we'll do something with those 10 results and then return to our normal sequential operation of our program. Well, one way we can do that is actually embedding the free applicative inside the free monad. So free applicatives give us basically the effect of parallelism. And free monads give us the effect of sequentiality. Think of these things as being, F is the operations that make up our program, and then these other structures give us a computational context, whether that's parallel or or sequential or whatever it is in which to execute them. They describe the computational substrate on which our operations are executed. And if we nest a free applicative inside a free monad, then great, we get this thing that I call seq par here. And we can take an f and we can lift it up into a seq par. And we can take an f of a, that is one of the operations, and we can lift it up into a seq par. And then we can take a sequential program, free fa, and we can lift it up into a seq par. And also we can take a parallel program fragment expressed as a free appf, and we can lift it up into a seq par. The global nature of our program is a sequential series of parallel program fragments in f. So we have little parallel program fragments expressed in f. Maybe they're singleton, maybe they only do one thing, and then we sequence them all together. And there's the code in Scala and yeah, both code. And then here we can define what it means to do, for example, optimization on these fragments, which would be useful for parsers and whatnot. Basically taking a parallel program fragment in one f and optimizing that to be a parallel or maybe even a sequential series of parallel program fragments in another G. So very general purpose optimization machinery that we could use to take those parallel program fragments and do a bunch of optimizations. Example of this is file system or network I/O or interactions with a database. Many of these databases that are distributed today, you can execute multiple requests in parallel and it doesn't slow them down because they hit different shards in a system.
What would be the G here?
It could be any G. Or it could be the same F.
No, I'm not just saying in this example you said, like with file systems.
Oh, with file systems. So if you wanted to, well, one thing you could do is you could execute multiple concurrent requests to read the contents of the file simultaneously.
But I would still be using the same language, right? It's all algebra. It was still the G would be F at this point.
Yes, that's right. So this is the fully generic. Okay. Because in some cases you may want to go from a larger algebra that has more things down to a more compact one by optimizing various combinations of the bigger.
Like the sugaring.
Yeah.
Okay.
Or like in parsing, maybe you would have that parse character operation, but you would not want to allow it in your lower level one, which is just parsing strings. How can we do this? Well, here's a, oh yeah, this is seq par. So what if we don't want seq par, but we want to do something else? Like we want to allow alternation. We want to allow our programs to fail. And we want to be able to go with the first program that succeeds. So we want to allow our programs to run and then fail down here. And we also want to be able to take two programs and try this one, but if this one fails, we want to do this one. How do we do that? Well, again, one way, by using this idea of nesting that we first saw with seq par, is we're going to create a new functor called alt, and it's either going to be a failure or it's going to be the first success among two free alt programs, or it's going to be a fact f of a. And then we take that and we stuff it into free, if that makes sense. Yeah?
I have a question. So I can see how the previous case you couldn't do it with like a co-product and then taking free, but I fail to see why you cannot take like an extra functor for failure and first success and make your co-product with whatever you want and then take the free. Why you need to nest these two things together?
Yeah, so the problem is that first success really wants to compose in order to satisfy the definition of alternative. It wants to compose at the level of the entire structure, the free monad. So right now it has a reference inside itself to the larger structure, the free alt. And even if you broke alt down into a co-product of these different things, which of course you could, then you're still going to have that reference to the larger structure inside itself. So basically an individual term inside this coproduct is going to know what the overall composition of effects is, because it needs to refer to the entire thing for you to be able to write an alternative instance for it. And I'll get to why that's an issue and a problem, but like when you look at this, you should be thinking to yourself, okay, free alt is free of alt. What is alt? And you look down there, alt is blah, 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 blah. Oh, alt has free alt in it again. So it's like this circular reference. And I'll get to why that's a problem in a sec. So when you do this, you can now have something that's more powerful than a free monad, and it has, you know, plus or alternative, or depending on your language of choice, and then you can use it to do these types of things through interpretation of this much more complex structure. So that's a partial win, right? It's a partial win. First we did it for parallelism, now we're doing it for another effect. It's a partial win. But we can improve this approach a little bit. Remember I said that first success down here references the superstructure. So it has to know about the superstructure, the type of the superstructure. And that's not ideal, because then we can't reuse it with programs that are smaller and don't have all the same capabilities. So the first obvious step would be, let's make that generic, and I do that here. Basically I say the first parameter to alt is T, which is the type constructor for the superconstructor. And then I abstract that away, so now alt doesn't know about it, and then free alt, when it uses alt, just needs to, oops, there's a typo, it needs to pass the free alt type into it as its first type parameter. So now it's responsible for tying the knot. And that's an improvement. You can see how it's done in Scala, where it looks like I actually got the type right here. Okay, so this can be done, and this is about as far as you can take this approach. You can remove the recursive reference and just push it into the parent. But then you run into the following problems. First off, how do these things compose? You know, ideally in our best case scenario, programs are modeled as tightly as possible. We constrain them. If they don't require sequential operation, we don't give it to them in their types. If they don't require alternation, we don't give it to them in their types, and so forth. And by constraining our programs tightly, we liberate the interpreters. And the interpreters are able to do wonderful, magical things because they have more knowledge of what these programs require. So we want to be able to, ideally, at the end of the day, have these fine-grained substrate of computational effects that we can combine together so we can lock our programs down to just the things that they require. And this approach that I've outlined here, this nesting, it sort of does compose, but it hurts my eyes to just look at it. I've got this case class here called myFree, which consists of hypothetical alternation and parallelism and race, racing conditions for whichever one succeeds first. And they're all nested in sort of this deep functor stack. And of course I'm continuously referring to the outer one and the inner one.
Brief question.
Yeah.
Do you consider that superior to aspect programming?
What's that?
Do you consider that superior to aspect?
No, probably not. Well, actually, at least it's type safe. So it may be hideous, but at least it's type safe. So there's a few problems with this. It doesn't compose very well, and even though it does compose, it will compose at great cost to performance because of all these multiple levels of functor nesting, and also usability. This is not easy to use, and I'm sure some magical whiz out there can make it easier for this to be used with type level machinery or macros or whatever, but it's not going to be pretty. Also, it sort of blurs the machinery it blurs the machinery that is the sort of computational substrate on which our program executes with the operations, the individual operations required by our program. They're all sort of mixed-matched. In a basic free monad, it's all very straightforward. You have your operations, and then you have the sequential computational context in which you embed those operations. And here it's all just a big blur. Where's the actual operations that describe our program? Well, you can't tell that from a generic type signature. You have to know the full sort of monomorphic type signature to know that it's n levels deep before you get to the actual functor inside our massive composition of functors that represents the effect of the program, and all these other things are just adding computational features. So here would be my wish list for such a construct. Ideally, we'd improve performance, and we'd improve usability at the same time, make this thing a little easier to use. And then finally, I'd wish for cleanly separating the effects from the machinery of computation. There we go. So, how could we do this? I'm going to cover one sort of precursor before giving you the full-on solution, and this should at least suggest the right path forward. And that is, we just construct our own free. We totally reconstruct our own free monad from the ground up, and we bake in as much stuff as we want. And using this approach, we might define a type called free star, which consists of an error type. These are the types on which our program can halt, so we'll make that explicit. And the effect type, the different operations that comprise our program, as well as a return value. So our program will ultimately either error, or run forever, or produce an A. And as it's executing, it requires the operations in F. It's the definition for Scala. Okay, so in the pure script case, I've given a definition, sort of one-pager, that just sort of lists all the possible things that this could be. And this data structure here is much more than a free monad. It's also a free monad error. It's a free, you can derive a different free applicative for this, or you can just sort of bypass that machinery and use the machinery for executing things in parallel directly. And I think that may be it. It may have other structure I'm not aware of. But this is basically just says, okay, we're going to go beyond just sequencing, and we're going to allow all these other things as well. And in Scala, this is how we would do it. We would have our type free star here, and then we would extend it with the effect of purity. This is a pure program. The effect of F, so the operations in which our program is comprised. The effect of sequencing, doing one thing and then doing the next thing that depends on it. The effect of parallelism, doing two things and then later combining those results into a single result. The effect of failure, which really only makes sense if you can recover from it. And the effect of doing the first thing, and if it fails, trying to do the second thing. So you can define all these instances. It's like I said, it's a monad plus, alternative, it's a monad error, and of course it's a monad applicative, and functor, and all that good stuff. And then you can use this and you can interpret it, and now suddenly your program becomes much richer. You can express all of these different things in straightforward fashion. However, there's a big problem, and we did not satisfy one of the earlier design goals that I mentioned. First off, our entire program has access to all features. That's not good, because remember, constraints liberate, and liberties constrain, which means that now even the tiniest program fragment that just requires parallelism now has access to the world of effects. It can fail, it can do all these other things. We want to lock it down. We want to only give that program fragment exactly what it needs, so we have maximum flexibility when we go to interpret it. And we can't do that with this type. It's just too, it's like the Death Star, it's the free star. It does everything in the world. Also, we can't express one feature in terms of others. And this, it didn't really arise in this simple example, but I do think that if you were to program in this style for a while, you would find some things that you would like to model as a computational structure which you can express in terms of others. It may not be easy, but you may want to be able to do that. You'd like to be able to use the first representation, but then later, at the bottom of your program, get rid of that in some fashion. Or maybe it's due to limitations in the environment, like if you have parallel program fragments that are not doing any network I/O, for example, and you're executing this in JavaScript, you can't do that in parallel, so maybe as some pass over that transformation, you eliminate those and decide which of those you're going to run first, those types of things. Using the Freestar approach, you can't express one computational feature in terms of others. It's just not it's impossible to eliminate them. You have to interpret all the features at once. So this basically means you're going to run into a certain level of difficulty writing composable interpreters because you basically have to interpret the whole monolithic thing at once. So what might we wish for? Well, ideally, fine-grained features only pay for what you use, so you can lock those program fragments down as tightly as possible. Also, compositional features. So if I do want to eliminate one feature by expressing in terms of others, I have that ability. And finally, compositional interpreters, which only handle a single thing. Maybe they translate from that into some target like I/O or something that you're going to run at the end of the world, but they only handle that one aspect, like they handle parallelism, and that's all they handle. And then, therefore, you can take that fragment, that interpreter, which only handles that single feature, and you can reuse it across everything else. So before we talk about how to fix that, I actually need to take a small detour and to introduce something that may or may not be familiar to you. So let's think about a very simple language for modeling addition of integers. And this is expressed using the type expr, which can either be a literal integer or it can be the sum of two other exprs. So very, very simple. The only thing we can express here is summing stuff up, summing literal values up. Right now, this definition of the type, it's recursive because we are referring to expr in the type expr inside one of the terms of the sum that defines expr. It's a recursive type. There's actually a way to eliminate that recursion, and it's called using fixed point types. You've probably heard of that before. What we do is, anytime we see that recursive reference, we stick a hole there. And in this case, it's called A, so you add a new type parameter, in this case called A, and any time that I previously saw a recursive reference to expr, I replace that recursive reference with A. And now I have lost the recursion. Now I can say things like expr of int. What's that going to be? Well, it's going to be, oh, that should be sum in that constructor. It's going to be a literal int or a sum of twins, and that's it. Those are my two possibilities. It can't have this tree-like structure. It's just a flat thing. However, I can regain that recursive structure by using a fixed point type. And this generic fixed point type called fixed here, basically what it does is it says you can construct a fix by having an f, a type constructor of kind star to star, and then inside there it's going to basically reference itself. And then you end up being able to recapture the recursion by using the fixed constructor on expr. So now my type recursive expr is actually a recursive expression that consists of all these sort of sums, and then they ultimately terminate in lits, or maybe it was a lit at the top. So those are our fixed point types in a nutshell, and it doesn't have to be super clear to you what this is about. Just keep in mind the procedure for doing this to your type. You introduce a new type parameter, and then all the recursive references you replace with that new type parameter. So that type parameter represents the self type, if you will. And then later you can recapture that recursion. And doing this has all sorts of wonderful benefits, by the way. it allows you to use generic recursion schemes. So you can write ways to traverse your data structure one time, and you can traverse them all day long, no matter what type of data structure, as long as they're expressed in this particular way. But also it has other benefits. You can lock down whether your data structure is recursive or co-recursive. So whether you break it down or you build it up. And also it allows you to define compositional data structures. So how many times have we been in a situation where we had like an ADT and we wanted to share that with another ADT? There's a good chunk of overlap. Like we had JSON, and then we had JSON plus one more term. And we wanted to share all those types and a lot of the machinery. And it's very trivial using fixed point types to do that. So they have a lot of benefits. I encourage you to study them. But we don't have time to go into that now. I'll cover one more case. And that is a recursive list. So this is a recursive list. It differs a bit from the preceding example. How does it differ? Let me show you the preceding example.
It produces a value and recursion.
Yeah, basically. So we have a list of A's. So it already has a type parameter. List is not a type, it's a type constructor. So that's the main difference here. So how are you going to fix this? We still need that self-type, right? But it's going to have a different kind. Instead of having kind star, it'll have kind star star. And that is because we need to propagate that information on the type of the elements of the list all the way through the stack. So we still have a self-type. I called it Z in this case. But now we need to encode that relation that ultimately that's a list of A's. So we just thread that A all the way through. So in this case, our definition of this fixed point type becomes a little more complex, but only barely. And then you can build all the normal sorts of things using this, and it's relatively straightforward. And of course, you would benefit in other ways if you had recursion schemes and whatnot. But there's no real point to do this for list. I would not encourage you. But we're going to use this same technique to allow us to make these free structures much more composable and fine-grained and satisfy our design requirements. Here's the same thing in pure script. Actually, here I just show you how this really does enable a new level of composability. So in this original example, I still have a sum type for list, right? It's either empty or it's cons. But I can split those two things apart. I can have lists that are always empty or lists that are always cons. And that's sort of the secret to making free structures composable, is being able to split out those different features independently and being able to combine them as necessary. You can do the same thing with a list. It's sort of silly, but at least it's a simple example. So in this case, what I do is I extend my list with a new operation. Instead of just it being an empty list or a cons list, it could be a concat list. So it could be the concatenation of two lists. So now I have basically prepending an element to a list. I have concatenating two lists together, and then I have the empty list. And then I define this coproduct-like structure, and then the fixed point type. And then what I'm able to do is basically combine these features to build a list that has whatever combination of features I want. And because this is all dynamic, I can eliminate features. For example, I can compile a list that is either empty or cons or concat. I can compile that to just something that's empty or cons. And how do I do that? I do that by expressing concat in terms of cons. And I recapture, even though these individual terms, which are now totally standalone, they're not part of a sum type, I combine them together using coproduct, and then I recapture the recursive nature of the list using a new fixed point type. So now I have a list whose features I can combine together. It's still recursive. I can combine those features, I can eliminate them at will. It's all totally dynamic, it's totally flexible. And in theory, I could do this all day long with even more features. And I might have parts of my program that use some features of a list and others which don't, and I can all bring them together or change them up as necessary. Again, don't do this. Don't do this with lists. There's no reason to do this, even though it sort of is. There are probably some performance benefits to doing this in some cases. And here's the same thing in Scala. The Scala examples get progressively more hideous. You will not believe the last one that I had. And here's how I do empty, colons, concat, uncolons, etc. Just implementing all these different cases for what I've defined as a list, which is recapturing the recursion on the coproduct of the empty or the cons or the cans. Concat. And same thing in Scala. Yeah. but this is not bad compared to what's coming. All right, so we have all the machinery in place to solve the problem now. What we're going to do is we're going to introduce a term that has the following kind. It's going to have a self type, which represents a program that terminates in a certain value. It's going to have that effect type, which represents all the different operations that make up our program. And it's going to have a return type of A. And actually, I'm going to take that one step further because I want to bake the error type into that. Because most programs, I think, will most likely benefit from an error type. And if we don't use it, there's a way to represent that. How can we represent the fact that no error can ever be thrown using machinery you've probably already used before? What do we substitute for E? Void. Void, exactly. So this is no loss of generality. It still allows us to lock down program fragments that don't throw exceptions simply by using void there. And same way for any of the other ones that we wouldn't use, like A, for example, if we wanted to represent a program that didn't terminate.
You have E used twice?
I do indeed. That's a problem, isn't it? That should be F. Sorry. I needed someone to proofread these slides, apparently. Nah. I did, actually, but I have the code in a separate repository. But I tweaked it once I got it in the slides. So here's how we do this. Now, every single one of these different terms representing computational structure are going to have the same kind. And we just sort of grab whatever we want and combine them together to encapsulate what that effect represents. In the case of purity, it's very straightforward. We just store a value of A, of type A. In the case of an effect, well, F describes the operations of our program, so we just do F of A. In the case of a sequence, it's a little more involved, mainly because, well, in the PureScript case, PureScript does not have existential types, so you have to scolomize those. That just leads to a little bit of noise. And the Scala example is just more verbose, even though it does have existential types. They're modeled a bit differently and it takes up more space. But this is basically bind. This is sequential computation. We have a program that produced an A naught, and we have a way to go from an A naught to a program in A. Then we just stuff all that in a data structure and call it done. Parallelism is a bit serial, or a bit similar. We have a program that produces a B and a program that produces a C, and then we have a way to join those B and C together to get an A. Just stuff that into a data structure. Of course, the effect of failure is modeled by a way to halt the program with an error, as well as a way to recover from such a halt. And then we have ordered alternation here with first success, which is just try the first one, and if that doesn't work out, then try the second one. Okay, and we can keep going. We can keep going all day long. We can add race conditions. We can add all sorts of computational effects that we like in the same fashion. And how we can combine these things together is with that little beauty. well, actually, the PureScript one's not too bad, but the Scala one is truly a gift. And then we define a fixed point type for this. And now we can combine all these terms arbitrarily together in any combination. We can have super fine-grained effects down here, and we can gradually expand them. And also we can take some effects and we can express them in terms of others. But the problem is that, basically. At this point, we have so much machinery involved that it strains the boundaries of what these languages were intended to do. You see that a little bit with free, but people have worked using macros and type-level machinery to sort of get rid of almost all of that, and as a result, it's not really a big problem for free. But for something like this is way more complex. And I know, I can't even imagine a way to solve some of these problems with Scala. Maybe it's possible, who knows? Someone else will come along and hopefully clean up this mess. Because right now it's really straining the boundaries. To program using those structures that I introduced would be really, really terrible. But you know, on the bright side, it's somewhat benign boilerplate in the sense that the type of your program is probably going to fit on 3 or 4 lines. But if you make any mistake, the compiler will tell you. So at least there's that. You probably can't go wrong, even though it's extremely painful and distracting and very noisy. You probably can't go wrong. And my hope is that people find a way to take this basic idea and make it actually usable. I am not optimistic, however. I would guess it's probably never going to be usable in the languages that we have today. My wish list would be for language level support for basically constrained heterogeneous sets, both positively constrained and negatively constrained. Because as I'm looking at a lot of these problems in free, that's basically the situation that we have is we're modeling these different features, and we're basically using coproducts or higher order coproducts in order to describe sets. And we would like to be able to say that this set is equivalent to this one, independent of order. We would also like to be able to express things like the set definitely has at least these 2 things in it. And it does not have this other thing in it. For example, if we want to express one feature in terms of another or express one effect in terms of another, we want the ability to eliminate a term from that set. And expressing that in today's languages is just not easy, and in some cases it's not possible. The other thing that I would really like is to be able to find a way to express recursion as a computational feature. In other words, embed basically a fixed point combinator, the Y combinator, inside a term. And require people use that for recursion. And the reason for that is that if you know that a program fragment is not recursive, and you have the ability to explore it in its entirety, it opens up new possibilities for whether that happens to be printing that program fragment, or translating it into another language, or optimizing it into a much more efficient structure. When you have the ability to sort of confine recursion to only the parts of your program that actually need that, then it opens up tons of possibilities on the interpretation side of things. And honestly, I think that the combination of these things really suggests the need for a different type of programming language that is geared at making programming like this possible and easy. So even though I encourage people to play with type level stuff and macros and all that other stuff to try to make this stuff simpler, ultimately I believe it's just too much. Our programming languages don't want to be used in this fashion. Even though in theory you would open up lots of new doors, and really they're pushing back against us. And ultimately we're going to scare developers away from joining our teams if we try to use the language in that fashion. So here are my closing thoughts. This is where we are today. Post-free is, in my opinion, about reifying the structure of computation, making all those things explicit. So you can lock down those parts of your program that require them, and that opens up doors on the interpretation side of things. By constraining the structure of subprograms, we liberate interpretation of them. And post-free is something that can happen today. Again, I wouldn't encourage it for commercial functional programming, but as something to play around with and sort of push around, I would absolutely encourage people to play around with this and see how far they can push it. And you can do it now using a variety of techniques. And only that last one sort of achieves all the design goals except for the usability and performance ones. But even the other ones, yeah, the big all-important ones. But even the other ones, you know, a free monad extended with alt, for example, could be super useful for a front-end library. Or in other cases, then that might actually be practical. If you're not trying to get all these benefits, just sort of one or two, then using your own custom free monad, basically the reconstructing free approach, extending free with another term or two, it's going to have good performance, at least as good as free, but it's going to give you that one or two extra things you need to write your programs in a totally different way. And where can we go tomorrow with this? Well, post-free points to a world where programs are defined by computational features, which are defined in terms of other features until you get down to some base set of features on your target platform that it can actually support. And also by defining program effects in terms of others. So for example, defining the business domain in terms of the REST API, a REST API domain, and defining a REST API domain in terms of network protocol, and defining network protocol in terms of calls to FFI, etc. And all this gives you the ability to do type-safe, sort of aspect-oriented programming, weaving features into your application, introspection of that program, and optimization of it as possible, even type-safe mocking, as we saw earlier. And it also gives us a way to give our programs purely denotational semantics in theory. If we've expressed our entire program as basically mapping between languages, these symbols have this meaning over here in this other language, then basically we're able to give a denotational semantics to our entire program, and then we're left with something that the runtime can deal with, for which there's a well-defined, you know, ideally well-defined formal semantics. So that's where we could go, and I think all that is most likely going to require language development. It most likely is not going to happen in today's programming languages. So that's it. That's all I have. If you have thanks, and if you have more thoughts on this approach, I'd be happy to hear them after. And I blog on DeGoes.net if you don't know. Thank you very much.